Alright, continuing with these series of videos, examining how conventional physics is explained at most universities, using Professor Lewin of MIT as a generic example. Something like that.
Into electromagnetic waves, I would like to discuss a few more mechanical resonances with you. Last Friday we discussed the resonances of string instruments and wind instruments, but there are several that
So again, resonance is, I think, essentially about this idea again, where when I was talking about magnetism and coils, that you're able to conserve the energy in the sense of keep it longer by creating reflections, and the reflections just keep going back and forth inside a container. And that's a kind of magnification or amplification of the energy, because you're not losing it. It just it's the ping pong ball trapped between the ping pong paddles. And so in a sense, you're putting some energy in ping pong balls, and the more of these balls that you can keep bouncing without breaking or losing their energy, losing their component that's trapped inside, that gets kind of that as an amplification. It's just louder and louder and louder. And so it has a minimums. I mean, it has maximums. You can't just keep collecting it and keep collecting it and keep collecting it. But because there's some friction in the system, some energy losses in the sense that two things collide and they don't reflect perfectly. They reflect imperfectly and create noise in the system and heat and movement in different directions that are all non-constructive to this idea that you're trying to create a lot of energy going back and forth at a consistent rate. So all the harmonics are basically things that travel constructively. That is, when two things meet, they're heading in one vertical direction, not opposite vertical directions. So their energy is conserved, most of it. There's some losses, but most of their energy in this direction is conserved, and so it remains as part of the reflection. It's transmitted back and forth. So that bit of energy is magnified. So the energy that is constructive stays in the system. The energy that's destructive is annihilated, and that's basically the resonance, in my opinion, as a overview of what the concept is really about. The concept is really about this idea of constructive interference, which is a real thing with the movement of atoms. It's not a real thing in the tiny world of nuclear bits. It's a real thing when you start moving nuclear bits.
you see around you quite often without realizing it, perhaps, that you're looking at a resonance frequency. You may have noticed that traffic signs have the tendency sometimes to do this, and at certain wind speeds they go like this. Enormously strong amplitude. That's a form of resonance. Undoubtedly you have...
Yes, and how resonance is captured, that is how you capture the energy at different frequencies, is part of this whole equation, where what really decides that is something's tilted a little. Something like, I think he's going to use some bridge that collapsed. And the reason why the bridge collapsed is because the resonance frequency had more to do with the tilt of the bridge. So as the bridge tilts at a certain rate, it's constructive to the way the wind was blowing through the channel of the ravine. So the wind was probably coming up at a certain angle, and so it just kept pushing at that angle more than it was pushing on one side. It pushed on the other side based on the wind direction. So it was, as it rocks this way, the wind kept hitting it this way and hitting it up and hitting it up and hitting it up, and that's really what's causing the pendulum to swing. I mean, resonance doesn't just happen. It happens in the sense of collecting energy at the right frequencies. You have to have something in to be able to keep it. So you can't keep the good stuff unless the good stuff is actually going in to the system. So the system has to have a bias towards that good stuff, or you'll have more noise than you will good stuff, and you won't magnify the good stuff, because you'll be too busy having destructive interference and creating heat and other things.
Being motels or at homes where you open the faucet, and then all of a sudden, when the water is running in a certain way, you hear an incredible noise, a terrible noise. You close the faucet a little, or you open it a little further, and that noise goes away. That's clearly an example of resonance. You drive your car, or someone else's car, and at a certain speed...
So the frequencies that are going to be constructive are very specific, and you do need to supply them to have any hope to magnify them. So if the system isn't supplying those frequencies, then it can't magnify them, it can't reflect them. So if you don't have any light, the mirror can't reflect the light. But if you provide the light, then the mirror can work.
Something begins to rattle. Very annoying. You go a little faster, it stops. You go a little slower, it stops. Or if you go a little faster, something else begins to rattle. There's some other resonance of something else in the car. Of course, there are cars whereby something rattles at any speed, but in any case, there's always this idea then of resonance, which is all around us. I remember when I was a student, and when we had an after-dinner speaker, which we didn't like, we would all very quickly empty our wine glasses. In those days, we were still allowed to drink, by the way. And what we would do is the following, something extremely annoying. We would...
You would be rude. He tells stories that really aren't very good stories. So apparently they were incredibly rude. So somebody bothers to try to make a speech or a statement, and they all boo, essentially, with their glasses, which is kind of rude.
Generate the fundamental of our wine glasses. You take your finger, you make it wet, and you rub it like this. Listen.
So the point is the glass has built into it a distance, a frequency. This is what I will reflect, and when I reflect that distance, the reflections will all peak at the right places, and they'll trough at the right places, and all be constructive. And other frequencies, though, will cause a lot of destructive and not be very useful in terms of magnifying the energy. So he has to put in a lot of frequencies. So by running his finger around, he's making a lot of different kinds of vibrations in the glass, and so he's supplying a lot of frequencies, and so there's some frequency, some portion of the frequencies they're creating are the ones the glass reflects without any destructiveness, and those are the ones you're hearing. So he's making all the other frequencies, they're just not magnified, so you don't hear them, but they're there, but you don't hear them. The only ones getting magnified, the only ones reflecting, maintaining are reflections. Going in and staying alive, going in, staying alive, going in, staying alive. So it, magnifying. No one's getting magnified through the retention of reflection. That's probably the precise way to say it. Through the retention of reflection, they're getting magnified in their amplitude because they're not being diminished. They're not leaving. They're staying in the glass and causing it to vibrate more, move more at that frequency.
Believe me, if 100 students do that, it's very annoying, but it's also extremely effective. Speaker gets the message very quickly.
Yeah, well, if I was the speaker, I'd fucking send you a message. Frickin' audience would be doused in something.
What the glass is doing, it is the fundamental of the glass. It's the lowest frequency. The glass is actually doing this. And there are rumors that people can break glasses by singing. We'll talk about that in a minute. I remember
I don't know why he has to edit that part, but it's just kind of funny. He edited it.
Commercial. Memorex. Memorex is an audio tape.
Yes.
And they bragged about breaking glasses. Some of you may actually have seen that commercial. There was a picture that I can show.
I don't think anybody had missed it, or whatever.
You that goes with the commercial, and then a very dramatic story. The story is that someone goes to a concert, and there is a woman singer, puts a glass on the table, raises her voice, hits the resonance frequency of the glass, and there goes the glass. And this gentleman was recording it, of course, on his Memorex tape.
So he's using the really old commercial from like the 70s, which is none of these students had seen. So instead of the guy in the lounge chair when his glass moves across the table, that's probably the one he should have used, but whatever.
So let's see this slide. So if we get the slide, yeah, you see this this glass. Maybe you can focus a little better, John. Thank you. See Memorex. So the story then goes that the guy goes home and tells his wife about this. Well, she is smart enough not to believe the story. But he plays back his tape. And at the moment that this glass breaks at the concert, he has some wine glasses himself at home. And lo and behold, they also break. And so then the idea is, that is the commercial, that's the great pitch of Memorex, that the reason why they break at home is because of the enormous quality of this tape.
Right, I think he just could have got to this much. He didn't need all this, like this is real grammar school explanation, a lot more detail than we need. So the idea that you can break a glass with sound, obviously, you know, it's got to be a very high amount of it you got to put in, even with magnification. So, you know.
It's made of very special material. And the material, as you could have read on the box, is a very special chemical compound. It is MrX2. 2 atoms of X, one of R and one of M, and then you make an oxide, and then you have the best tape that you can imagine in the world. Well, they overlook a small detail, and that
there is no R and X atomic structure, so I don't even know what that is, but whatever. MrX, Memorex, you know, I don't know. I mean, there's a chemical compound. I think it's just mostly iron oxide, but whatever.
That is that, for one thing, a tape recorder would never generate enough volume to break a glass in the first place. But in the second place, the glasses that this guy had at home obviously didn't have exactly the same resonance frequency as the glass at the concert. So this would never have happened. But like with all commercials, you know that you're being swindled, and this is, of course, no exception. I've always questioned whether it is actually possible that a person, without the aid of strong amplification and without the aid of huge sound volumes which you can generate with loudspeakers, whether you can actually break a glass. I've always wondered about that. People say it can be done. Caruso, famous singer, was known for being able to do that. He put a glass there, he would rub it with his finger so that he knew the resonance frequency, and there he would go and bingo. Frankly speaking, I don't believe it. I don't believe it can be done by a human being without the aid.
I think it can be done. You just need a really crappy glass, right? So you need a really, really thin glass. So if it's a thin enough glass, crystal, you know, so it's got a little harder structure in it, you know, less liquid, more lead, yeah, you probably can. But it's going to have to, yeah, you got to make a glass that's made for breaking. Very thin glass. Damn, I wish this keyboard would work better. It's just really annoying.
Amplifiers and speakers. And when I lectured 801 several years ago, together with Professor Feld here at MIT, we discussed the possibility of designing something that actually would be able to break a glass. And he actually deserved a lot of credit for that. He worked with a graduate student, and he managed to design.
I'll try it one more time just to see if I can get this to work. No. I mean, the keyboard really should work. It's just annoying. Anyway, sorry to be, I'm being annoying, talking about it being annoying. Just be nice to get the keyboard to work. Try clicking
setup that
here.
Works most of the time. But don't put your hopes too high, it doesn't work.
There, now it works. Okay, so there's a trick to it. There's always a trick.
All the time. So here's a wine glass, the same series as that one. By the time when he got it to work, we bought 500 of those glasses. We got a good discount, by the way, because we wanted to be sure that we can do it for years to come. So here's the wine glass, and here is the loudspeaker, and we're going to generate sound very close to the resonance frequency of this glass, which we have already determined before you came in, 488 hertz. You're going to see the glass there, and to make you see actually this wonderful motion of the glass, we will strobe it with light at a frequency slightly different from the frequency of the sound, so that you see the glass move very slowly. And then we will increase the volume of the speaker, and then with some luck, if we are right on resonance, the glass may actually break. I think this is the sound that you're going to hear at low volume. And I think I turned on the strobe light now. So I'm going to make it dark. And I want to warn you that the sound level is going to be quite high. I will have to protect my ears, and you actually may have to do the same. I will first...
No, it is interesting to see, just as you get to see this idea that this is a liquid in a sense, that this glass is not as, I mean, it can do an awful lot of moving, without breaking.
Increase the volume of the sound to see whether I'm close enough to resonance. So this slow motion that you see is the result of the strobe, which is not exactly at the same frequency as the glass. I can change that a little. All right, so we are very close to resonance. The glass is clearly responding to the sound. And now I will cover my ears and slowly increase the sound volume.
So the idea, as he would say, is to pump in a bunch of frequencies, deliberately trying to put in the one that's going to reflect without destructive interference. So you maximize the number of reflections happening, and if you can maximize the number of reflections, you can increase the amount of energy, total energy, that's bouncing around inside that glass. And when you make it big enough, if you get enough reflections that aren't destructively breaking down in some way, creating unnecessary things like heat and other stuff, you'll just create more and more pressure, and finally enough pressure to break the glass, enough movement. When you look at that, it's an awful lot of movement, You just would think, and there's no way a glass can move that much. But it can if you're moving each individual atom, and you're not trying to move just one section. Every little single atom's being moved by the energy moving around between the atoms.
Can't go any louder. Tough glass.
So anyway, they could do that with slow motion nowadays, and make it even better. But that's pretty good.
It was a tough glass. I think you will probably agree with me now that for a person to do that without electronic help is just not so believable. The most dramatic example of destructive resonance is the collapse of the bridge in Tacoma in 1940.
So again, you just use the word destructive, but it just means destructive in the sense that it broke the object. But clearly it's constructive in the sense that this resonance is all about energy that has a large component in the same direction, so it's preserved, versus energy in opposite directions that is not preserved, that cancels out. So it's really about constructive interference that creates destructive magnitudes of energy.
Many of you may have seen that dramatic movie, but some of you may not have seen it. And even if you have seen it, it's worth seeing it again. There's a little bit of wind. There's a little bit more wind.
I think it's
just like with these
copyright.
wind instruments, you're dumping a whole spectrum of frequencies
They might not let him show it because of copyright. It's kind of funny.
onto a wind instrument, and it picks out the resonance frequency. And this bridge, as you're going to see, picks out its own resonance frequencies. And the consequences are quite dramatic. So if you can start, Marcos, with this movie.
Dawn of a fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile-an-hour gale, the center span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now. There's an automobile caught on the heaving roadway.
So the trick is that the wind has to be coming at a direction, so it's pushing one side more than it ends up pushing the other side, and it just keeps doing that little by little, and that it keeps adding frequency in one direction and not adding it equally in the other direction. So there has to be an unequal addition of the energy in the beginning to cause the capture of the right frequency.
The 11,000-ton center span twists and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick.
So I guess my point would be is that when the bridge is designed, they're not really, maybe they're just not, they don't think about it, but they're thinking about, well, how does it face the wind in one direction? They're not looking at the aerodynamics. So what happens if the wind comes from underneath the bridge? What if the wind is coming from a certain direction? What will happen? And that's sort of the failure here, is not to anticipate that the wind wouldn't be just blowing sideways.
No structure of steel and concrete can stand such a strain. Steel girders buckle and giant cables snap like puny threads. There it goes! Engineers are divided as to the cause of the disaster. Some claim it was the use of solid girders. Others differ. But whatever the reason, Tacoma will rebuild. This time a bridge that will not provide a super thrill in the news.
No other example of destructive resonance is more impressive than this one. All right, so now we've had so much fun, and we have to really get into electromagnetic waves. So we turn back to...
All right, so he leaves this nice subject of mechanical resonance that's happening between really atoms transferring energy, the big pieces of the nuclear bits, the electrons and stuff. And now he's going to get into what are these things that are described as fields, but this really we're talking about photonic style energy, the energy moving at the speed of light. The forces moving at the speed of light, like gravity, magnetism, and light. And charge, of course. Charge is magnetism.
Maxwell's equations as you see them here. And Maxwell, who was credited for this extra term that he added to Ampere's law, the displacement current term, was able to predict that electromagnetic waves should exist. He predicted...
So again, just totally uninteresting prediction. This is they already knew about infrared light, ultraviolet light. They already knew this light spectrum thing. Newton had already done this with the prisms separating. We had figured out that that's a frequency of light. So all of that was already known. So you knew that you had light at 300 nanometers, and then you had lower frequency light, and that you had the higher frequency ultraviolet, and you had even higher frequency X-rays. So they already knew they had 10 nanometer X-rays, and you had light at 700 nanometers, and you had infrared at 300, no, at 1300, or whatever the number would be. And so you already knew you had all this range. So predicting that there was something below or above in terms of length, that there were still longer ones to find, and there might be shorter ones still out there, like the cosmic rays. Not exactly anything we should applaud. I mean, that is so just sitting there saying to you, it's like two pieces of bread, just saying, oh yeah, you put some jelly or peanut butter, you put some whatever, lunch crap, you put some cheese, you spread some butter, mustard, whatever. You make something out of the sandwich. It's just screaming sandwich, right? Two pieces of bread just saying sandwich. I mean, it's just obvious.
The existence of radio waves, which were later discovered by Hertz.
So yes, so it took Hertz 7 years, because the trick is the only way to detect these lower frequencies, just like detecting with our eyes, you have to tune. The system has to be tuned to it. So you have to create a tuner. So they had to create an oscillator, with an inductor and a capacitor doing that push-pull thing, to be able to create a mechanism to filter out all the frequencies you don't want, so you can magnify and amplify the frequency you do want. So until he did that, we couldn't detect the radio waves because they aren't visible and they don't affect electrons in as dramatic a way as photons, visible light.
And that was a great victory for the theory. But as I will show you today, there was another enormous victory around the corner. Electric and magnetic fields can move through space.
So again, it is described as this enormous victory, enormous thing, and it's just as plain as day, sitting there just saying to you that yes, you have this much of a scale, and there's plenty of room on this side, and there's some room on that side. Of course, you're going to sit there and look for the things on this side and the things on that side,
and satisfy all four Maxwell's equations. The electric field results from a changing magnetic field, and the magnetic field results from a changing electric field. The one exists at the mercy of the other, and the other exists.
All right, so they're the same thing. So they're this idea that there's two fields. There's only one field. The field is created by changing the atoms in a substance and charging them. And you can charge them into a dipole that we recognize as magnetism, or you can change them into a monopole that we recognize as charge and that we call electrical. But it's really the same thing in the sense that you're creating a surface that is either electron heavy or proton heavy. You're changing the shape of an atom, which makes it either radiate more proton energy, or it radiates or reflects more electron energy. So you're changing whether it's like a mirror. You can have a mirror that reflects blue light and a mirror that reflects red light. So if you thought of it that way, you could understand that when the atom is changed, compressed or expanded, what's happening is you're changing it from a blue mirror into a red mirror. So now it'll reflect only red light or reflect only blue light. And what it reflects, just like in the resonance circumstance, means it magnifies what it reflects. So, that's why magnetism is a thing. It relies on reflections. That's why it appears to be extra force. It's not really extra force. It's just conserving the force that goes in doesn't escape. So it traps force, therefore magnifying its effect.
At the mercy of one. Together they propagate through space. They can even propagate through vacuum, where there are no charges and where there are no currents. Very mysterious.
Very not mysterious in the sense if you understand that they're just photons, virtual photons, and they're just doing exactly what gravity does in the sense that it's it does everything like it's a ray force, a straight line force. It mimics the consequences of a straight line force coming from the outside. And magnetism is just basically saying I'm taking this energy coming from the outside and I'm trapping some of it. And by trapping it, I create more and more reflections on the inside. I collect ping pong balls between the two paddles. Then the paddles have more and more pressure.
I will write down a possible solution of an electromagnetic wave, which meets all four Maxwell's equations.
Sorry. Didn't mean to do that. Just trying to get back to keyboard.
Display of those waves that I'm going to write down, but I will discuss that with you.
Right. So it's not a graphical display. It's a graphical display of a mathematical model. And so the real world, it isn't doing any of that stuff in the sense that there's none of this stuff. It's a compression in a linear form. So it's, high pressure, low pressure, high pressure, low pressure. It has there's no extra length to any of these lines that this implies. The thing is moving the linear distance, and it's just an amount of force at those locations that they're describing with these this grid. But this grid isn't a representation of three-dimensional space. It's a representation of magnitude in a different not a material three-dimensional space. In the real space, you draw it as a clump. A big clump, little clump, big clump, little clump. Dark clump, lighter clump, dark clump, lighter clump. You draw it as a line, okay, with gradients in it. Dark, light. Not like that.
In a minute. The electric field is only in the direction of x. This is the magnitude, the largest value of the electric field. It's only in the direction of x. Cosine kz minus omega t. This is the frequency, and the minus sign tells you that it is traveling in the plus z direction. B,
so they have their two constants that they've now applied, called the electric constant and the magnetic constant, their epsilon zero stuff. And those two constants add up to the speed of light. So you can sort of see that they're already, in a sense, conceding that these two fields add up to the one reality field where things move the speed of light. So it's almost saying those two fields always exist. There isn't one field or the other field. It's always just the one field. You're just interpreting the one field in one circumstance as being pink, when it's really all the same field. It's not pink and white. It's one field.
Associated magnetic field is B0, only in the y direction, with exactly the same cosine minus omega t term. So if I plot...
So there's no y direction and x direction in the reality. These x and y do not represent up, down, and left, right in any way. So this doesn't have anything to do with reality. It has to do with their conception, and their conception has misidentified the one field as two separate fields. And in one circumstance, they'll say one field doesn't exist and just the electric field exists. And in another circumstance, they'll say there's no electric field, it's just a magnetic field. But it's always just one field. There's only one force, and it's a field of that force. It's an amount of force.
This at time t equals 0, then you see this curve right here. And you see the magnetic field curve here. The magnetic field is only in the y direction, and the electric field is only in the x.
There's no x and y direction.
Direction. And this is a package that together moves in the direction of plus z with this speed, which is omega divided by k. And the wavelength from here to here is then 2 pi divided by k.
And k has the constant in it, which is the speed of light.
We call them plane waves. And the reason why we call them plane waves is that if you take a plane anywhere perpendicular to z, that no matter where you are in that plane, at that moment in time, the E and the B vector are everywhere in that plane the same.
I would argue another huge deception of this is when you have a bunch of photons, they will average out to maybe a sinusoidal wave of intensity, just because of subtle irregularities in their phase. They'll be a little out of phase, and so you might get something like that. But the truth is the photon is on, there is one or there isn't one, in the sense that it's a clump of energy, and it's a group of clumps makes a ray, which we call a photon. So a photon is more than one piece of energy. It's a few corpuscles of energy in a row. a stream of bullets. Bang, 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 bang. There, photon. You need more than one for it to affect electrons and cause them to resonate, essentially, and then readmit the photon in a new direction. But they're clumps, so in the reality, there is no sine wave to a photon. It hits, complete hit, as Feynman described. And so I don't think Feynman was very comfortable with this description of a photon, because I think he knew that it's very clumpy. And it doesn't gradually hit something. It doesn't slowly grow bigger and stronger. It hits, period. All at once, everything. There's no, I'm showing up, I'm playing, I'm pushing, I'm going through a process. The process is in very, very tiny amount of time it takes, and it's a complete interaction for which there is no graduation. There's no gradually creating the photon's energy. The energy is peaked, peaked, peaked. It's bullets. It's clumps. It's corpuscles.
So think of this as a plane perpendicular to the z-axis, and then this whole train passes by you. And so you see the electric field vector like this, becomes 0, like this, becomes 0, like this. And the magnetic field vector, maximum, 0, this direction.
So the funny joke is the two fields are active at the same time. They're on at the same time and off at the same time. And that's essentially one field.
And so on. But that's why they're called plane waves. These equations only satisfy Maxwell's equations under two conditions. And one condition is that B0 is E0 divided by C. And the other condition is that omega divided by K, which is the velocity with which it propagates, I will call that C. In vacuum, we call the velocity of electromagnetic radiation C. If that is 1 divided by the square root of epsilon 0, mu 0.
There you go. So you have the epsilon 0 and the mu 0, which are these two numbers that they constantly use in Maxwell's equations to define either the speed of the electrical component or the magnetic component, and they're basically combined. Those numbers equal the speed of light, 1 over the square root of those numbers. But regardless, that combined they account for the total speed of the force. So even if your electric field is 0, it still has a speed, and that speed ends up getting dragged into the equation one way or another. So it wasn't any. There's no huge insight in the sense that the epsilon 0 and the mu 0 were contrivances. They were invented terms, and that those invented terms are really describing the real truth, which was the force moves at the speed of light. That was the truth underlying it from the very beginning.
If that's the case, my two equations will satisfy Maxwell's equations. Imagine the victory for Maxwell. Maxwell was not only able to predict the existence of electromagnetic waves.
So again, this is just more history, put in some bizarre context. It's like the Young experiment, totally unremarkable. Newton had already discovered, fringe patterns. Nothing, this wasn't anything new. And Maxwell now is being credited with some kind of discovery of radio waves, when again they're made obvious by just the discovery that light was coming at a frequency. As soon as you knew light had a frequency, you knew it was just obvious to go, what's that way and what's that way? Just obvious.
But he was even able to predict that they would move through vacuum with that speed.
Again, everything moves at that speed. So everything was being well discovered that all the stuff we thought was instantaneous, anything that we might have had a notion of instantaneous, that there was no spooky action, that stuff, this is before Einstein, Maxwell. So let's understand, spooky action at a distance wasn't an accepted way of things happening. It was only the way they understood it. Newton didn't have an explanation, but he clearly understood that spooky action isn't the definition of the reality. That any reasoning person knows there must be a mediator, there must be a mechanism here. It's not just happening for no reason. It's happening and in some ESP way. It's happening in some mechanical way, and they just hadn't discovered the mechanism. By Maxwell's time, they were discovering the mechanism. They knew the mechanism moved at the speed of light, and that these other forces were doing exactly the same thing. Gravity and magnetism and charge as a force were all moving at the speed of light. And that should have told them, there's our unification theory. There's the unification. So let's forget about Einstein and say, yes, look, we have our unification theory right here. In the fact that there's a thing causing all these forces to have exactly the same speed. And just rationally you say, well, that's because they're probably the same force. They're made of exactly the same thing, just in a different form. The same exact thing, just at frequency or not at a frequency. Polarized or not polarized. I mean, the answer was just jumping at them. Like the two pieces of toast, saying, do something with me. And they did nothing. They cut it into little squares and threw it in soup. Bent space soup.
What an unbelievable victory, when you come to think of it, that epsilon 0 can be measured in a static way.
So again, it's never been measured. These constants were not measured constants. They were created constants.
From Coulomb's law. It has nothing to do with stability, it has nothing to do with the unity. It has nothing to do with traveling waves. Epsilon 0 is about 8.85 times 10 to the minus 12 in SI units.
Right, and it was created out of the necessity to make just like Newton's big capital G, it's a constant created out of necessity to put this force into a unit that matches the actual units of pounds and miles per hour. And to make the equations work, this is the constant you needed to make them work. And this constant times plus the other constant.
Mu 0 is equally static, can be measured from the force at which two wires to which you run a current attract each other. No dB, no dEdt, has nothing to do with electromagnetic waves. Mu 0.
Again, not a measured force, a force recognized to create conservation. You have to conserve the energy, and this is the constant that allows the energy to be conserved.
Is about 1.26 times 10 to the minus 6 in SI units. And if you multiply them and substitute them in this equation, you'll find that C equals 2.99 times 10 to the 8th meters per second. Unbelievable. What a success for that theory.
All right, so again, out of necessity, out of the fact that any experiment done over a period of time would have to recognize how fast the force was moving, how fast you could collect it. So it was a necessity that the speed of light would have to come out of this somewhere, because the fact is your equations aren't going to work if you don't get the time of the force right, how long it takes the force to get somewhere. So it was out of necessity that they would eventually have to find the speed of light. And they found it with two manufactured constants.
It always baffles me how two quantities so static and seemingly so unrelated to moving waves.
Unrelated to anything real. The permeability of space, a completely made-up concept. Again, now they're renaming them the electrical and the magnetic constants. So, and they're only doing that because they still are stuck with these two fields, and so they have to break the speed of light into two fields. But there's only one field, and that's why, and it has stuff moving the speed of light in it. It doesn't have stuff moving mu 0 or stuff moving epsilon 0. There is no stuff moving epsilon 0. There is no stuff moving mu 0. The only force that moves is the one going the speed of light, period.
With dBdTs and dEdTs all over the place, how they can predict the speed of light. Suppose I ask you to measure the pressure in your tires of your car, and I would ask you to also measure the voltage of your battery, and then to predict the speed of the car. It's almost something like that.
No, it's absolutely nothing like that. There, it is so in the ducks are so much in a row. And again, this is an example. They can't even describe their own history correctly, and have just this canard that somehow these were numbers that came from inspiration when they came from necessity.
It is bizarre, but it works, and it was a great victory, and of course it justified entirely this one term, which is this displacement current term. Together, you and I will prove that this is indeed a necessary condition so that these equations satisfy Maxwell's equations. We will do it together. I will do 50%, and you will do the other 50% at assignment number 9. So we split this bill 50-50.
So all he's going to do is a bunch of elaborate derivatives. Okay, they're going to start in one form or another with the two half constants and create the final one constant, and it'll just be a bunch of contrivance.
I will make a new drawing, and I will do something that I rarely ever do in lectures. I will give you 8 minutes of hardcore math. You're going to hate it.
Yes.
I'm going to make a new drawing, which is not too different from what you have there. So this is z, this is x, and this is y. And at t equals 0, I'm going to draw here the electric field, like so. So this is E0. Electric field is this strength. And now I'm going to apply.
So let's understand, there's always just one field. Always. Always.
Ampere's law, that's my half of the bargain. Closed loop integral of B dot dl, you see there, equals epsilon 0 times mu 0 times d phi e dt.
So there you have the two constants multiplied times each other, which is basically saying 1 over c. Yeah, in a sense.
We're dealing with vacuum, so kappa m is 1 and the dielectric constant is 1. And there is no such thing as a current I because we are in empty space, so this whole term does not exist. What does Ampere's law require? I need a closed loop, and I need a surface that I attach an open surface to that closed loop. I'm going to choose a closed loop in the plane yz. And this is going to be my closed loop. This here is going to be my closed loop. This length is L, and the length, or the width, this side, is lambda divided by 4. I have to do a closed loop integral of B dot dl. I will do that last. I will first do the hardest part, which is the time derivative of the electric flux through this surface. The problem is that the electric field is...
So I just understand, this flux thing doesn't only exist in this chaos. You have to have a field of many photons, many bits of energy for this to have any meaning whatsoever, because in the reality, all you're really talking about is you have a full portion in one tiny corner of that loop. And that's the only one that did anything if it's a single photon. And it existed, and then it won't exist until it hits again, and then it'll exist again at the bottom of the loop, and then it'll exist again at the top. And again, one looks like it's minus and one looks like it's plus, but no, that just means there's a bit, there's a bit, there's a bit. The zeros are the only, those are the gaps between the bits.
Is not constant. The electric field is 0 here, and has a maximum here, and falls off in this way. So I have to do an integral. So I'm going to make a slice here. And this slice here has a width dz. And in that very narrow slice, the electric field is approximately constant. Right here, the electric field has this value, but everywhere in that slice, it has the same value, because remember, it's a plane wave.
So again, these are just averages, so it has nothing really to do with what the individual photons are doing. It has to do with what the average will be when you have a bunch of different rays coming out at different angles.
So I will draw here a line parallel, and so everywhere in that slice, the electric field has exactly this value. And that value is given by this equation. If you tell me what z is, at time t equals 0, I know what that value is. That's this value. It's enough.
So now we draw the same thing in the other plane going this way with the magnetic field, I assume, but whatever. We'll find out next time. So, I think, yeah. So anyway, till that next time, and such, and so forth and whatnot. Yeah. See you soon. Such.